Hey, I need to make a 474 intro transition. So here we are. We might have anyone here. Hello. Let's put hello in the chat. So people might be watching this later right here. I saw Joelle and other people earlier. So we've got the support vector machine lab. If you jump into the chat, feel free to say hello. Hey, Joelle, what's up? So good to see you in the other chat right there. I had a meeting earlier, so I was in the meeting and then I was doing their thing. So I joined a little late on there. So sorry I'm a little late on this right here. But let's start talking about some support vector machines, and feel free to ask questions if you have them in the chat. So we've got right here all of our packages that we're doing right here. We won't have to knit this. Their red classes working. I think a lot of people get really afraid when they see this right here. And Joelle, you can hear and see me perfectly, right? And Evan, hey, Evan and Joelle, everyone can hear and see me, right? I'm always afraid. I don't know. I've been streaming for a long time, but we had that one error last week. Good, awesome. So just last week when I streamed to the wrong video, and everyone in the chat's like, "We can't see you," and everyone else is like, "Hey, Brian, hey, Brian, can you hear us?" I'm making sure all these are running right here. I do have that one. Cool. These masks, what masked means is something is using the same function. So we have right here like number of variables and alpha right here are being used by other things. So that's what masked means. So we have everything is just because people use the same names for functions. So those are all the masking means. Good to see you, Evan. Good to see you, Joelle. And so let's go right here. Load in the EX3 abalone data, a fairly straightforward data set dealing with the size of these sea creatures. They are a delicacy, and we want to build a model that predicts the meat weight. So once again, one thing I like to do is make sure you know the code before we get to it, because a lot of the code is given to you, but we should know how to load in a data set that's already here. You can load in data sets with this right here, but I want to see it in the chat. I want people to slow down and think about this. There's a huge hint, million points, and points are working again in the Streamlabs, but why can we load this data set in right now? Why can I instantaneously load this data set? Why am I able to do this and not like do read.csv, which reads a CSV file? Why am I able to do this right here? Why am I able to do this? Any ideas? On why I'm able to just do it this way and not some other convoluted way of read.csv, read.xsl, xlsx? Why am I doing this right here? And the reason is this is a data set. I'll probably say it because only a few people watching. This is a data set that is inside. Good, Joel. Thank you so much. Million points, Joel. I just like the responses from people. Maybe you do get those Streamlab points for checking your points. So this right here is a data set that's inside of reg class. So you notice how it says reg class where I'm hovering over with the cursor right now is because this is a data set that exists inside of reg class. There's other data sets. I think the way you can look at them is you can run this right here, or you run it with the open parentheses. And now these are all the data sets that are inside of R. So we could load a data set like, let's go right here, fires. Fires is inside of best GLM. So if I were to do fires right here, you'll notice fires is a data set that's inside of best GLM. So since I have the library best GLM up, it's going to be able to give me that data set. And then I've loaded that data set. Promise means it's loading in. It'll eventually appear. But data set fires is a data set. So we can take a look at it right here. There it is. Now it appears. And there's the data set we just loaded in. And yeah, that's it. But if you see this data function being used, it's for data that R already has loaded into it. You might still have to load in a package like or a library like red class though. So we want to look at meat weight. Let's look at meat weight. Meat weight right here is how much weight they're getting off of these creatures, I guess in pounds. And so there's not a ton. I mean, if that's a pound, that's not a lot. It might be, I don't know. I was going to say kilograms or something, but that might be a horrible measurement maybe. It's in kilograms, I think I'm like 70 kilograms. So a kilogram is what, like 2.3 pounds or so? Might be about that. Sounds about 2.3 pounds maybe is a kilogram. 2.6 pounds. 2.6 pounds is a kilogram maybe. Someone told me in the chat. Okay, so we know what's going on with the data. We know what's happening. There's the same thing. So I've already done what it asked me to. 2.2, there we go. Evan, million points right there. Thank you. And so, yeah, it would not be 70 kilograms. That would not. We can just do some quick conversion. We just do, 70 times. I know, right? Brian is not that right there. Brian's closer to like 85 kilograms. Yeah, about 85 kilograms. So there we go. But yeah, definitely not 70 kilograms. We've got the data going right here, and then we've got the head of the data just to make sure we got it, but we need to make our trained data set. Okay, so I made a mistake last class, not like a major mistake, but it wanted us to use like a certain sample size. Now, one thing you can always do is you can go to your data with caret thing. I'm going to write this out right here. I'm going to do the actual thing myself just for practice. It's always good to remember how to do this. Train.rows is going to be a random sample, and the random sample is going to be 1 through the number of rows of our ex3 abalone data. What does this first part of the code do? It just makes a number line of all the numbers. That's all it does. So it's all that is 1,528 numbers. Like if you looked at this right here, we can even store it into something like, what is this? And if you look at it, it's just a number line of all the numbers. So you don't do that. I mean, you don't have to turn this in, but I just wanted to see what it is and put it here for me to see. It's just a number line of all the numbers. It's just an integer number line. So we'll go here next, and then we need to tell it what percent we want. So the first argument is, what are you sampling? So argument 1 right here is, what are you sampling? And then argument 2 is, what percent do you want, or how many do you want? We can do it as a percent by doing the following right here. We're going to use nrow again, because now we've said take this many right here, and it'll take that many right there. So when we create the train rows, it's going to create a random number set of that many. We need to use a set seed here, which we often like to put these side by side like this. That's just appending the code onto it. And now we've got appended code that whenever I run this, you can see what my train rows are right now. Here's my train rows. You see that 493 right here. I'm going to rerun it now with the seed. And now when I rerun it, the 493 is now 1390. But when I rerun it again, you are right, Joelle. Thank you so much. Don't forget that set seed. When I rerun this, we get the same answer. So the importance of set seed is you get the same answer every time. Set seed controls the randomness, so we know what we're going to get. We're going to take the train rows right here, and we're going to go to train, and we're going to go to ex3 abalone. We're going to go inside of it with the square brackets, and we're going to take the train rows. So that code right there, we're going to copy this code. We're going to paste, my favorite way to do that. We're going to say not the train rows, and we're going to go here and do the holdout. And then we're going to check our head of our train, and we got it. The sanity check works. Oh my gosh, when the sanity check works, that's just like, we need a meme on that when the sanity check works, and someone just like, sorry, it's a theme of this semester, sanity checks not working. So perfect stuff going on right here. Does this make sense what I've done? I've just created my training and my holdout. So holdout, well, train looks good, the holdout should be good. Yep, we're good. Everything's great. So other sanity checks should work too. So the pairs function right here is going to let us see the relationship between multiple variables. And it's so interesting. Joelle was talking about how she misses 201, and I hope she misses 320 also, because the pairs function is something we learned in 320, and all we're going to do is take the meat weight, which is the y variable, and we're going to plot it with all the x variables. There is an advanced way with correlation matrices. There's a package I found that made them look really nice, and I can't remember the name of the package, so we're not going to get to see that. But there's a correlation. I hope someone finds it and sends me, like, I don't know. There's a bunch of people who send me stuff. They're like, hey, Brian, check this out. I'm like, oh my gosh, you guys figure out so many cool things. Uh-oh, is this a big correlation matrix? Yeah, it's pretty big. So simpler times when we just had to do like one graphic and one variable. This is 320 again, though. This is 320. Let's take a look at what we got going on right here. It's going to take a while loading this graphic, even on, I can't believe this computer's having trouble with it. Don't crash, computer. There's a, well, there we go. I noticed quite a few things with this. So let's go across. I want to say why I'm choosing this. I'm choosing to go across these graphics right here. Why? Why are these graphics right here the most interesting to me? Ren, did you tell UT alumni to contact me? Oh, yeah. I think, did they contact you? Did they contact you, yes or no? I've had a lot of people asking me to contact different students for different things. So, maybe I did tell them to contact you, or did you want me to? Because people be like, we want to interview students, and oh, they wanted a picture. Yeah, I guess because maybe they interviewed you. They did. Yeah, so because I told them you had experience with like an online class, because a lot of people are wondering how we're doing this right here, because everyone's been very positive, and I'm very thankful, and I really love how you guys can interact with me and interact with everyone else. And Andrew, look at this. What do you notice about like some of these, especially, I've changed the green screen a little bit today. We've got a little bit of what going on right here. I see a little bit of heteroscedasticity, especially over here, some heteroscedasticity. Ooh, look at this. That's a huge outlier right there. Major leverage point. Yeah, Minnie asked the question away, and we'll put it, I'll answer it right here for you too. No worries, Minnie. So you notice right here, this is a huge outlier in the graphic. I guess it doesn't follow the relationship. If we follow the model, but that's a huge outlier. We don't like points like that. That's something crazy going on. If you're wondering what I was asking, why am I looking at these graphics on top only? Does anyone know I'm only looking at these graphics on the top row? Because the y variable at all times in the top row is meat weight. So the y variable right here is meat weight on all these graphics. So this is meat weight versus length, meat weight versus diameter, meat weight versus height, meat weight versus whole weight, and then my head's blocking the last few. There's that one, and there's the one behind it. So you can pause the screen right there and see what those graphics were. Like there's rain or something like that. How do you know the third condition to use? And I was doing the project on the first part, got confused on whether yes, Minnie, great question. It's on based if the data is categorical or quantitative, and I did that at the very end of the last video. So look to see if it's quantitative or categorical. If it's categorical data that you're doing, like fail or safe, then it would be success failure. If it's quantitative, like how many days, it would be nearly normal. Does that make sense there, Minnie? And it's at the end of the last video, in the last 10 minutes or so, I think I did. You'll see me writing the conditions out. So that's too funny, Andrew. You're welcome, Minnie. So we've got all this going on right here. We see, Andrew, do you see the nonlinearity to this relationship right here? So you know what this tells me? There might be some sort of polynomial dimension to the data, or maybe we'll see what happens with the support vector machine, but we're about to do some really crazy stuff here, Andrew. So we're about to see some really crazy fun code. But I see here some non-linearity to it, non-linearity with the Y, outlier, heteroscedasticity. So this is not the cleanest and best looking data. We're not too happy with the way everything looks right here. Oh, yeah. Got 320. Yes. You'd be like, I was just looking at some data right there. That's so awesome, Andrew. Support vector machine uses a kernel trick to project the original data into a higher dimension. My 474 should know that instantaneously. I can't tell you how many times I've said this. That support vector machine will bring us from like a 4-dimensional data set to a 5-dimensional data set. It accomplishes this feat by implicitly creating new variables. It finds some combination of them via an equation that gives components of the kernel something like a distance matrix, which is an only quantity needed to determine the form of the model. It then finds the best linear regression to fit the relationship, with the catch that the coefficients are chosen to minimize the sign of the absolute values of the errors beyond a certain threshold. That's our epsilon right there. So that is one of the things we can control. That's a tuning parameter. So we should know right here, this is huge. With the catch that the coefficients are chosen with certain beyond a threshold. So this is our epsilon. Try to explain as much of the relationship as possible with as little information as possible. Exactly. Choices we need to make are the kernel, linear polynomial, or radial basis, which is Gaussian. So here's your 3 things, and you don't really tune this. So people being like, well, is that a tuning parameter? It's a different model. It's not really a tuning. I guess you could say you tune on it, but you're just picking it. So the cost for making errors right here, which is the epsilon, and then we've got the kernel specific, which is like the radial basis has a sigma, and the polynomial has a degree. So that's that. There's the radial basis has its tuning parameter. So there's kernel specific tuning parameters. So really, how many tuning parameters? Oh, these are mean questions. I need to write more questions for our test coming up. How many tuning parameters are there for the radial basis? How many? So a 474. How many tuning parameters are there for a radial basis? I'm kind of giving some hints right now. When you do a radial basis, how many tuning parameters do you need? You would only need, careful, not only, but you'd only need what? How many tuning parameters would you need for radial basis? Radial basis needs a million points if anyone gets in the chat, who knows? Radial basis needs this many tuning parameters. A radial basis would need 2. You need a cost. You don't need it. I mean, you have to put it in, but you can tune it as much as you want. You'd have a cost, and you'd have the sigma, which is used for the radial basis. The polynomial has how many tuning parameters? Once again, it has 2 because it has a cost and it has the degree of the polynomial. A linear kernel has how many tuning parameters? 1, because the linear kernel only has the cost. So we have this right here. Let's try them all using caret, and let's try all the predictors. You spend a lot of time on the tuning grids, but I'll save you some time coming to tuning grids decent. The process right here, use the fit control here. Okay, so once again, and I hopefully am not going through this too quickly, it's just something we've done a lot. When you see this right here, you should know what this fit control does. This fit control right here is going to use cross-validation. It's just using 5 k-fold cross-validation. We could do repeated k-fold. Might try that here in a moment. But with this validation right here, we're trying to see how our model works on the validation, which is our estimate of how it'll work on the holdout. That's so key. So this line of code I'm currently on is what controls the validation of the model making, and it's how we think it'll work on new data. Not how it actually does, that's the holdout. This is how we think the model will work on new data. So we're just creating the fit control right there. We've got an expand grid with the cost right here, so it looks like we're making the linear kernel. And so let's go ahead and, sorry, we've got here the support vector machine grid right here for there's the grid for the other one. And these are 3 different grids. Okay, cool. So we've got our 3 different grids right here, which are set up properly. If you notice, we got the degree and we've got the sigma right here, and then we've got the cost. Once again, there's only one tuning parameter for the linear kernel. You can see the one tuning parameter here. We've got 32 different models. I must have ran another model. We've just got the cost. And now let's take a look. There we go. There's 7 different models. So this is the polynomial. Creates all the combinations of models we are trying. And then we go right here, and here's the last one with 32 models. So these are all the different models we are creating. So I'm going to go ahead, and I've already got it pulled up. I'm going to go ahead and pull up the code right here. Let me see, I've got 2 different chats pulled up. So let me close out the other chat so I can make sure I'm always in our chat. And let's take a look at the code we need. Okay. So sorry. And let's go down here and let's take our code. So let's go, and we can do some little changes to this afterwards. We just need to change the name of the method. And there we're inside of R. Let's put our thing inside of here. And there we go. We're going to make this code look all nice because that's always our goal, to have a nice looking code that's easy to read. And then let's interpret the code. How are we doing in the chat? Who we got here? So probably lost Andrew. He's probably in class now. So let's take a look. We're going to go here to y tilde x comma data equals. I always like putting this one first. I might do the data equals second right here. And then we've got support vector, or we got data equals. We've got support vector machine linear, which we'll just change that to poly next, and then we'll change it to radial next. And then we've got the grid, and then we need to go into here. We got the tune control. We've got the verbose equals false, which controls the output, and we've got the center and scale, which turns things into z-scores. So I can't state this enough. You should know what every part of this code does. Once again, you can copy paste your code all the time. I highly suggest copy pasting because you're going to see me just copy paste this code. But take a look at what we have right here. We have set seed, which controls the randomness. We're saving into support vector machine linear. We've got here the equation y tilde x comma data equals. Well, y tilde x, we're predicting the meet weight. And then we have here the dot means all the y variables are going to be used. Data equals train. Make sure to use your train data. The method is support vector machine that chooses the method inside of the caret package. We've got the tune grid equals support vector machine. Once again, or support vector machine grid. Oh, there we go. Now we have the right one. Good thing I checked that. Good thing I checked that. And then we've got the tune control equals fit control. That's what we made earlier. That's the fit control we have up there. We've got the verbose equals false. That controls the amount of output we see. It's like someone who's very verbose like me. We're going to say, don't be verbose. Just give me the limited output. So we're saying we don't want to see all the output. And it's rather fun if you turn it to true. Your screen just floods with output. And then we've got the pre-proc, which is the pre-processing of the data, which is going to center the data, which turns everything to a mean of 0 and scales the data to a 1, or if a 201 or 201 her is in here and answers what things are with centered and scaled. If they're centered and scaled, as in they have a mean of 0 and a standard deviation of 1, I'll max you out on points for the semester. Let me do it for 474. By center and scaling everything, everything's going to be turned into a what? Like this pre-proc right here is going to put everything on the same playing field and turn everything into a what? Who knows? 474, 201, 320. I can't give 320 points because I'm not teaching them. But what does pre-proc turn things into? Pre-proc will turn things into this. When we pre-process the data, it's going to make everything into this. Everything, if they have a mean of 0 and a standard deviation of 1, they will all be z-scores. Well, careful, Joel. I'm still throwing you. Joel, you're here. You're the only one talking. You get the points. Only a transformation would turn things into a bell-shaped curve, or could attempt to. So transformations will attempt to turn everything into a bell-shaped curve. I was kind of making a bell-shaped curve because that's the hint, it's z-scores. But if you make things have a mean of 0 and a standard deviation of 1, they'll be z-scores. But how to achieve normality? Normality is achieved through transformations. So you can make things normal and they wouldn't be z-scores by transforming them. Does that make sense? Like if you transform something, the data might look normal, but data that is z-scores have a mean of 0 and a standard deviation of 1. They don't have to be normal to be z-scores. You can make anything z-scores. It won't make the data normal. It just gives them a mean of 0 and a standard deviation of 1. So this literally right here, this code right here turns them into z-scores. So that turns it won't. That's a really good. So Zach, good. So good to see you, Zach. That turns them into z-scores. If you know, Zach, we're even talking 201 concepts right now about z-scores and bell-shaped curve. So all this good stuff, and points do seem to be working again. Streamlabs, you are awesome. I worked on stuff this weekend. We've got. Just get ready for it. You ready? Oh my gosh! Just use your imagination right here. Just use your imagination right there. Just imagination. I gotta have a better lead in for that. Love you some z-scores and bell-shaped curves. You're right. We use them all throughout. You're kidding me. Oh, we did it. I got the imagination. It's again to see it now. I've got it. I worked on my setup. I can put an echo on my voice and everything too. Okay, so so we go right here and we take a look at what we got. Let's take a look at this. Let's see what we got. Sorry, I know my code looks crazy now. Here we go. We're going to plot it. Did I already run it? I did not run it. So it'd be good if I ran the code. Code runs. Code's awesome. Code's great. So now we're just going to plot it and see how it did on finding these models. Okay. So what do we want here? We want a very low RMSE, because we should know from 320 that RMSE is typical miss the model makes, and it looks like our best model is somewhere. It could technically be inside of here, and I won't, you know me, I'd like to change my tuning grid and take a look at what's going on inside here. It does look to go down as the cost goes up, and if this is the best model, I want to know what happens if I put an even higher cost parameter on it, but definitely somewhere over there. Let's take a look at the results of the best tune right here. We'll change our window again, and let's take a look at the results of the best tune right here. So let's take a look, and the cost of 1, oh, so there, yeah, if you can't, yeah, you can see right here, that looks to be the cost of 1 is the best, and I have to see it. I can't let this go. So, did I use the right grid? I feel like my grid's wrong. From negative, oh, because we used the 10 raised to. Did I use the right grid? 10 raised to, yeah, -2. Yeah, so I'd use this. It's more tight in there. Let's do this. I have to see it. I have to know if I can make a better model. And I'm just afraid of using the wrong grid. So I really want to see what's going on in that area right over here. I'm blocking it now. No, I want to see what's going on in this area right here. This is my main area of concern right here. And it is kind of bevying out in there. If you notice, we get this area right inside of here, which seems to be close to 1. So 1 might still be the right answer. I'm going to switch it back. But, oops, there we go. Okay, cool. So I'm pretty happy with the way this turned out. I couldn't do really much better. If you'll watch, the graphic won't change that much. I'll go this way a little bit more. Graphic's really not changing. 1 does seem to be a pretty good answer right here. So we're not getting much of a return when we increase the fine nature of the tuning grid. Like we could search real choppy with a 0.5, or we could search really finely with a 0.1. And so we go right here. There's our best answer. And so the typical miss the model makes is 0.03 on the new data when it predicts the meat weight. We get an R squared of 91%. 91% of the variation is explained by this model. That's amazing. Let's see if we do better. What I'm going to do, and I'll tell you what, watch this. I'm going to take this data right here. I'm going to call it row 1. So let's store this as row 1, and we're going to try something here in a moment. So I've taken this as row 1 right here, and I'll see if I can do something. This is what I would highly suggest. Cool. No, that's not what I wanted you to do. Will that work? That worked. That worked. Sure. I'll fix that at the end of it. I don't like that it says linear at the top. I'll fix that. Okay. So let's fix it right here. What is it? Names row 1 type. And then let's go here and go, it's got the linear in quotes. Let's go to position. What position is that? 1, 2, 3, 4, 5, 6, 7, 8. There we go. Did I miss a parentheses? I saw a weird coloring. No, maybe not. Well, now it worked, and now we take a look at this right here. Cool. Okay, that's got it fixed. So now all we're going to do is just take our code right here, and we should just be able to change it to the poly. And you know what? We can take all of this code and we're just going to fix it. So we're going to go here, and there's the support factor stream grid. I'm going to put the second right here just to make this make more sense. There's your tuning parameter 1, which is the degree. And we've got the C right here, and we've got the scale. So we've got all of it. We're using a scale tuning parameter 2. And let's go here and put this in here. So now we need to change this to, this is the poly, I believe. Yep, it's got degree, so it's poly. So now we should be able to, we run this, and we go ahead, we'll go right here, put this right here. Right again, run the poly. Poly seems to like it. Now we're going to take our support. I overwrote my linear. No. There we go. Well, now it's gonna, we'll fix it. We're gonna fix our code while we're doing this right here to just be the right code. And we want this now to be poly, and then that'll overwrite that. Okay, so we're gonna have to rerun this code right here. Here's our tuning grid, and then we're gonna set this, we're gonna run that. Then we're gonna plot it and take a look at it to see what's going on. And this will be our polynomial kernel right here, seeing what's happening with it. So let's see what's going on with this. It'll take a moment to run right here. And I said that last time, a lot of these take a little bit of time. So, yep, okay, we're good on this. And I want to call this row 2 before I delete my row 1. And I think we're good. Here's the plot of it. Oh my gosh. So, 0.1, it's hard to tell. The answer is somewhere in here. So it's very hard to tell with all the graphics where the answer is. It's kind of between a few possibilities. So let's look where the best answer was. There is the best answer right here. And we probably won't be able to stack these because we would just report them all in sequence. We can't stack them because they're not the same type of stuff. So gotta learn how to do some binding of data sets better. But the R squared here is actually lower. So you can look at the RMSE or the R squared. We probably want to look at RMSE because we're looking at RMSE for the last one. Let me pull up the last one real quick right here because I've got it stored as row 1. And if you look at the RMSE of the last one, the RMSE of the last one is a little bit lower. And it might be, let's go ahead and add 1 standard deviation to this. Let's see okay, this is the bigger one down here. So I'm seeing if these two are similar. And all I do is I take this right here, and I add to it 1 standard deviation, and I see if the original or the poly one is within 1 standard deviation of the larger 2 RMS standard deviations. And it is. So this model right here with an RMSE, this is the polynomial model. Got it right there. It's the poly model. Is similar to this one right here. We don't have a clear winner yet. I mean, I guess I would go with the linear model. Sure. There's no real reason why right now. It was first and it did better, but it's within 1 standard deviation of the other one. So I don't have good reason. So what we're going to do once again is we're going to take our code that we just wrote and, oh, did I not? I overwrote. And then let's, yeah, so row 2, it should look, yeah, there we go. Oh, haha, I overwrote that with type. That's an error. We'll let this code run in the background again. It's not the same row. We will grab this right here. And we're going to go down here to the radial basis kernel. We're going to check our things here in a moment. And let's go right here, and let's call it radial. And let's go here, and it should be SVM radial. It should be capital radial. So this should run right here. We need the grid for it. So we've got our tuning parameters right here. Boom, tuning parameters are done. And then we hop right here. We run this. Code seems to be running, so it likes it. And then we're going to change the name of these codes down here. And we've got it right here, radial, radial, and then this will be radial. So we've got our codes right here. We're good to go. We've got the plot. We need to change this to row 3. And let's take a look. And it looks like the red with the high sigma, the high sigma is better. And it looks like we're not going below 3. So radial basis doesn't look to be winning out. So let's see what it said here. Radial basis has an RMSE of 0.305. So that's actually maybe the lowest. We can compare it to the first one right here with the 1. The RMSE of the first one was 0.306, but these are very similar. All models are coming out with very, 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 very similar results. We are getting the sanity checks. We get the MAE standard deviation right here, which is this one. and we could check our polynomial. Here's the linear, and we see here that the linear has an MAE standard deviation of this. So we're getting all the sanity checks, but one big thing to note, and probably, so you know what I could do? We're gonna try writing a code here because we're nearing the end of this. There's really, and I can't reinforce this enough, the comparison between models is so key that you need to look at this data and know what it means. Like we always talk about in tool one, like what does this all mean? We've got here R squareds and stuff like that, so it's percent of variation explained. Which model is row one? That is my linear model. Row one is the linear, row two is the polynomial, row three is the radial basis. Great question right there, Joel, million points. What I'm gonna do is I'm gonna go to row one. I'm gonna go here to RMSE, and we should be able to report the RMSE. Cool. So, and let's do the following. And so we're going to take all of these right here. Here's all the RMSEs. And just thinking of how to make, well, then it'll be a vector. Let me sort that way. And then there's a command to turn things into columns. How can I turn the vector? Yeah, this will work. This will work. This will work. I got it. So here's my RMSEs. I see how to do it. So here's all my RMSEs. So there's all my RMSEs. And then we're going to take all my RMSE standard deviations. And so RMSE should have an RMSE standard. There it is. Looks like it exists. And then we'll go here to type. And it was linear, polynomial, and radial basis Gaussian. So we've got all this right here, and then we go to data frame, and then we go to RMSEs, and then we go to RMSE standard deviations. If you can't tell, I'm putting all of these in here because then we can view them, and it'll autocorrect for you. And ooh, what happened here? Oof. Should not. Let me look at my RMSEs real quick. What is going on? Oh, that's not good. That's why it's looking like that. So let me think. If I go here to, would not be row bind. Look at that. Okay, there we go. There we go. There we go. Got it. Okay. There we go. So now let's do one other thing right here. Let's go to row names, df, and there we go. Okay, there we go. We got it fixed up. Does this make sense right here, Joel? We can take a look at it this way, but here are my RMSEs for the model. We can sort it nice and easy now. We can see the radial did the best. We could even do a confidence interval on this, where we could take and we could do a comparison to see if these models are similar. But this is what I keep talking about I want people to make, which I know the assignments really don't clearly say, like, make this thing right here. But if you look at this right here, you can see that all the models are basically similar to each other. All the models are within one standard deviation. The radial did the best. The linear did about the same. The polynomial did a little bit worse, but they all did within one standard deviation of the best model, which was so we could do that. We could write a code right here. Let's do this. We could go right here and write min of our data frame RMSE. So here's the minimum RMSE, and that was the one that did the lowest. And then we could do plus max of data frame $ this. And so that's the one standard deviation right there because we're taking the maximum. And anything basically at 0.32 is within one standard deviation. So you can see right here, all these models are below this threshold right here of what we would say are identical. So there's there's no difference between any of the models. All the models work about equivalent. We don't have any good reason to think that any of the models work any better than any of the others. Evan, great question right there. All the models work virtually identical. There was no big difference. It just depends on the structure of your data. Like you'd say, well, why did we run all three? You don't know what the answer is going to be. You don't know until you do it. So you don't know that they're all going to work at the same kind of like, well, I guess they all work about the same. And they do. They're all within one standard deviation of the best. So there's really no key differences between these models. It's like, well, they're all about the same. And so that's got that right there. Using the support vector machine with the radial basis kernel, make predictions on the holdout and make a scatter plot right here. So do we already have it? I already gave you the code. So let's go right here. All we're doing is predicting with this model. We're predicting on the new data right here. Boom. Support vector machine radial not found. So we didn't call it that. We called it another name. So I called it, I think I just put a capital R right there. So watch out, your model's not called that. It won't work. And now it works because we put in the right name for it. And so yeah, double check. Yep, we got it. And then we want to go right here and plot it. And let's see how it works. Not too bad. If you notice the problems with this model, and I'd say we chose the radial because it did the best. I mean, if they're all the same, you're right, Joel, no statistical difference. The z-scores are like 0.6, and it's like, well, they're all basically identical. If you notice, we still see some heteroscedasticity in here. So here's our predictions, and here's the actual on the holdout. Remember, this was not, but here's the thing. Did the model work decently on new data? I mean, this is what it predicted the new data would be, and here's what it actually was. So it looks like the predictions were actually pretty decent on new data. So especially down here on the lower end of the model, we just see a heteroscedastic relationship going on with this model, that the model gets weaker as it goes out. It's just there's more variation in the data. So we weren't able to like fix this right here. We weren't able to figure out why, but yep, that is it. Let's try a classification problem. We have to set up models to tune on accuracy. So because support vector machines don't naturally output probabilities unless the rest of the model's algorithms exist that come up with a good guesses of the probabilities, but you have to take them with a grain of salt. We'll use the wine data set. We're going to predict the quality of a wine, but we'll also forego splitting into train and holdout. You can come up with a good model that predicts wine's quality right here. Let's try the linear and radial kernels along with some sensible tuning parameters for each one of these tuning grids and make a plot of each object created by train. So train is the function we're going to use right here. Is there non-linear relationships in visualizations of the variable? So what it's doing is it's trying to trick it into being a linear model. So I can probably pull up the notes right here. Like if you think about what it does, is it takes the data. And so let's see right here. We'll go back to the notes and we'll take a look because it really shines when you see what's happening right here. So where is support vector machine? Here we go. So this will help us see what's going on. Okay. So it goes away. Cool. So it takes this data right here, Joel. So this is what it's doing is it's taking this non-linear data and it's going to find a trick that we're going to add some extra dimensionality to this data set that's going to make it linear. So we will be able to fit a line through this by adding in this extra dimension. So the extra dimension right here, which you notice is the X transpose right here, or transformed right here. So it's going to take this data that's nonlinear and find some sort of equation for an X variable through the kernel trick that will then create a linear relationship in some higher dimension. So what's interesting is we're just looking at the predictions right here. We're not looking at the higher order equation, but it found some sort of linear way to make predictions based on this, and it's able to fit in this line, which we can then like view a projection of at a higher dimension. So we're viewing kind of this almost like a 2D sense right now, but it's in a third dimension right here. So we're viewing just a projection down. I think that's the correct mathematical terms. Does that make sense, Joel, right there? That we're going to take this data, we're going to use the kernel trick to create some sort of equation that's a trick to put this into a higher dimension that will cause a linear relationship in the data. Does that make sense right there, Joel? It's pretty crazy stuff. It's basically, let me make it an easy way. It's writing a new equation for a new variable through the kernel trick that allows us to create a linear relationship. And that's what we're doing in regression. You also see the parameter right here, which is controlling at what point we start to penalize ourselves. And then we can have a certain cost right there and everything. And sorry, we noticed that was being covered up. I don't know why that's covered up. So I hope that makes more sense. Keep asking questions in the chat if you have it. The theory stuff is very important for the test. Like, don't just know how to run code, know the theory behind what it's doing and why. Okay. Let's see. We're going to go ahead and grab some code right here. How do you write the PostResample function? So the PostResample function takes two things. It takes both the y hat and the y. So I think you need the y first. You need y, then y hat. We'll take a look at a PostResample here. We're in Labs 9. So if we go here and write the PostResample. So here's PostResample. And let's drop it back into here. So we've got the lobs right here. Just taking a look at the PostResample for just a moment. We're just going to drop it into here to just start it off. the PostResample function takes in it the y variable and then the y hat. So the y hat is very similar to the code you saw just up here because this is getting y hats. So you could, if you notice this code right here, you could use this code right here as a guideline of how to write your y hats. And all it's going to take for PostResample is the following. PostResample is just taking the actual. So what is the actual value of meat weight? And then what is the predicted value of meat weight? So we've got here, and this is from a k-nearest neighbors. So this is the predicted value right here. So all PostResample is taking, not calling it prediction, predicted. So when we go right here, and we need to go to our support vector machine radial. There we go. Let's use the radial. And so we can change this right here to the actual. And we can change this right here to the predicted. So all PostResample is going to take for us is this right here. And then there's how it's working on the holdout. So actually, hey, that was a great question right there, Evan. It works extremely well on the holdout. So this right here is doing great on the holdout. Did just about as we expected. You know what's really awesome about this is I can change my model right here really quickly to support vector machine linear, and I can just rerun it here with the support vector machine linear. We chose the polynomial, which did the best. Now we're going to choose the polynomial before seeing how it's doing. And excuse me, we chose the radial. That was the radial. And then the polynomial did about as good. So if you look at this right here, or I did the polynomial, so we need to do the linear. And really, wait, linear and polynomial did the same? Am I going mad? I guess they did. That's really crazy. But unless I'm going crazy right here, that says support vector machine linear, that says support vector machine polynomial. And then the radial did better. There's the radial right there. So that's how it's written. Does it make sense what's the components of this right here, Evan? That the components for the PostResample are your actual and your predicted. And you can save your actuals, which this predict function takes the model you're using and predicts on new data right here. So does that make sense there, Evan? Are you pretty good on that? Does that help out? We'll see. I need to talk in the chat more. I need to get more points. I think we're good on that one right there. So now what we're going to do is we're going to actually be predicting and using accuracy. How do I know we're using accuracy? Because if you notice here when it says class probs equals true, that means we're using accuracy as opposed to, let's show the other one, with a two-factor summary. Let's go here. And let's go here to to class summary. Here we are. So this right here is when you tune on AUC. So there it is right there, AUC tuning. So you can use this one right here. It doesn't hurt to copy paste these, but you do need to know what they do. So this one right here is just accuracy. This one right here is going to tune on AUC, ROC, which they're the same thing. So we go back here to our lab, back. And let's take a look. We've got that we're creating our fit control. So don't worry, that's just a graphical error right there. It's because I have the windows too small, I believe. And then we go back here. We'll make our window a lot bigger. And we've got our fit control. We've got our parameter grid right here, which is going to be the cost. And then we just simply need to write it. Awesome, Evan. Glad to hear that. So we can probably just take our code from above. Why not? Let's go ahead and go back to our code where we have our linear kernel to start. So we're going to go back here to the linear one. And we're just going to take our code, everything. I think this is good. We'll just take all this code. And there's only one thing I should have to change right now. There's only one thing I should have to change. What is the only thing I have to change right now? Does anyone know the only thing I have to change? So it'll be up in here. Quality. Quality is the only thing I'm changing the prediction of. Once again, this is why copy paste is awesome, is because you cross your fingers, you go ahead and run it, and you run it, and it says quality not found. So we're, because we didn't create our train data set. Oh, it said don't worry about creating a train. So we'll do the problem as is. This problem said don't worry about creating a train. It wants us to use the full data set. Just we're skipping a step to just, where was wine at? Where's the wine? Did I not load in wine? Data, oh, it's the wine data set. There's an EX wine data set. It's capital wine, right? There we go. Cool. There we go. There it is. Tuning grid should have column C, so it doesn't like it. Should have column C. We do have column C. Oh, we called it parameter grid. There we go. I was using an old tuning grid. We called it parameter grid. So as you can copy paste code, syntax changes, so you got to change what you got. So now it's working. So always read your error, be like, okay, what's going on? It didn't grab the right tuning grid. And I do see a big error very commonly that this is a little c. It's why I love my copy paste. You should practice writing it too, but I often see that people put a little c there, and then if you put a little c, it's like tuning grid should have column c, and you're like, well, wait a minute, it does. And once again, it said we should get this error. If you look here, the line search fails warning, so that's fine. You should be able to make this not appear by going into a suppress errors or suppress warnings. So we're good on this. We've got it. Let's look at what happened here. We only got that many. So the cost parameter, I want to increase this. I'll run it as is. I'll do it as is. But the best model is clearly going to be this one. You know what? I don't want to increase it. These are such small differences on the accuracy. Oh, wait a minute. Wait a minute. That's not the best model at the bottom. What am I saying? The best model's here. Now I really want to increase it because I want to know what's happening in this area. We're doing accuracy now. You have to flip your mind because accuracy, you want the model to be predicting as accurately as possible. We were just doing ARMA-C a second ago, and you want ARMA-C to be as small as possible. So we want to increase the accuracy. So this is the model. We are choosing, that looks like a 10 or so. Let's see what it is. So that is going to be, yeah, that's 10 because this is 1, or that's 0.1, that's 1, that's 10, that's 100. And so we could go more finely right here. So a sequence from this to this. So from, yeah, let's do this. And let's go by 0.2. Okay. I want to know the answers to these. I want to know, like, how good these models look. And I want to know where we should pick it. We'll flip our answer back here in a moment. But what I'm doing by changing and adding in this is from this, it's to this, and by this. If you notice, these basic codes we do in 320 are used again. So all I did was add in a by statement and control the fine nature by which this graphic will be done behind my head. So this graphic right here is going to be made a lot more finely. There's going to be more breaks in it. There's going to be more areas for me to check, which is very important. So this is what I like doing. I like seeing how it does because I want to know if we can get an even better peak. I don't like how jagged this is. Like looking at this graphic right here, I don't like this jagged jump from here to here. I don't know the nature of the model in any of these areas connecting. I don't know how the model's doing in here. I don't know how the model's doing in here. And there might be a sudden peak, or it might be the peak over here. I'm guessing that the peak is somewhere in here. So let's take a look and see if I was right that putting a more fine grid on this, ooh, that's interesting. That's weird. That's so crazy. There's so much. So the peak is around here. That is our best model. And then it just gets crazy. This is probably just due to the uncertainty in this area. There's probably just a lot of a standard deviation in that area. And if you notice, we're not getting much return. This is not a rather large scale. It's 82.3% accuracy to 82.7% accuracy. So the difference in accuracy is only about 0.4, but when you're that close to 100, hey, never hurts to get closer to 100% accuracy. So what is our best model here? Well, once again, let's change it back. There we go. We got it fixed. Okay, so our best model here, and everyone should be getting the same models, is going to be the model with the cost of 10. We see that. We should get it in just a second here. 3, 2, 1, let's go. This one shouldn't take as long because I put a smaller tuning grid. Once again, everything, the reason it takes a while sometimes is because I'm checking all of these models right here. I'm running all these models on the validation. So when I plot this, here's the models, and we do get that the, we stored it. So let's just take the best results today. So here we go, this. And we don't have the right, okay, cool, we're doing the linear one. The cost of 10 is the best one, and we're getting the sanity checks. We're good to go. The accuracy is this, and I suppose, yep, we're going to go down to another model right here. So we've got all of our code ready to go. Let's just grab this code again, and we're just going to take the code down to here, drop it in. That's the radial basis. So let's not do the radial basis first, or we're doing those two only. Cool. And then random forest. Cool. Okay, so we're going to go here, and we're going to change this to radial. We're going to change this right here to radial. We're going to copy this right here. We're going to put this into radial, 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 and support vector machine radial is not part of, oh, haha. Support vector machine radial. There we go. Tuning grid was not changed. Tuning grid's changed. We're good to go. So once again, be careful writing your code. I'm doing a lot of copy pasting. It's a good way to make an error. And so you can see all that stuff right there. But once you have your tuning grid down, you should be good to go. And so now we'll take a look at how the support vector machine Radial is doing. We did change the name of it. Let's make sure we get the right name on this. So it should be Radial. And let's go here. Okay, that's all changed. Now we should be good with our code. So once again, we're going to plot this, and we're going to see how it looks inside of here. We're going to see how the model actually does, and we're going to get an idea where the best model is. So once again, you should know that this cross-validation is our estimate of how it'll do on new data. We're looking for high accuracy. And whoa. Oh, we're doing RMSE. What went on here? Let me think here. We're predicting quality. Something happened here. Something weird happened. Brian made an error. Oh, you know why? Do I not have the right model saved? Oh, you know what I think I did? I know what it is. It's this. Aye. There we go. So what happened was... we're gonna have to do that. Cool. So what happened was, my previous model was called support vector machine Radial, and my brain said, wait a minute, what went on here? Because this is tuning on RMSE, which is for quantitative data, and we should be tuning on accuracy, which is for categorical data. So we are tuning on categorical accuracy right here, and here we go. The best model right here, and we are looking at it is the cost of 10 with a sigma of 0.316228. And it looks like it's this one right here. That is the sigma. It's off the screen right now, but the green line is the sigma with that. There it is right there. And there's the cost of 10. So all in all, the best model is right here, which has an accuracy of 87.5%. And our previous best accuracy, oh. Anyone in the chat? 87.5% compared to 82.56% or 55. This is a vast difference from the previous model right here that had an 82.55, and the accuracy standard deviation shows us that that's not even 1%. These are like probably like, I'm trying to do the math in my head. These are like 8 or 9 standard deviations apart. These are worlds of difference. So the Radial is winning out right here. Sorry, I misspelled you, Radial, but you are winning out by far. The Radial is doing way better with this tuning on it. So I would definitely start refining my search on the Radial. The Radial is way better at predicting the quality of wine by about 8 standard deviations right there. We've got our tuning grid for the forest right here. So cool. So we got our tuning grid, and let's check it out. So let's go ahead and grab our code and change our code around. So once you have the code written, you're like, people told me one time, they said, the end of the course is so much copy paste. I'm like, well, yeah, that's what coding is a lot of times. A lot of copy paste. You just change this to random forest. That's how we do random forest right here. And we have our tuning grid, and we're running it. Now, oh, no, I overwrote it. No, I didn't. No, stop. Hopefully I didn't overwrite it. Cool. Now, I ran one line. I read that. Nope. If you highlight one thing and run it, it'll run just that one thing. Let's go here and do that. Well, crud. And then we go here. Random forest, random forest, random forest. Okay, so now we've got the random forest we're trying out. We're trying out using 3 to 5 different... We didn't do a forest grid. I mean, we did one, but we didn't do a lot. Very small random forest. Is random forest going to win? You know what I might do? I might up this random forest here in a second. Why you do that random forest? For anyone who knows why I'm just like, well, okay then. Well, who knows in the chat what I'm going to, of course, check now? I have to check something after I check a random forest. Well, one, the random forest just destroyed the support vector machine Radial. The random forest almost has a 92% accuracy. So the random forest is doing way better. The random forest is just destroying it. So what do? Let's go grab a finer tuning grid for this random forest. Let's look at our random forest. So you can't choose like 3.5 because this is the number of variables being used. So this is as fine as it would get. It looks like 4 is the winner. I mean, maybe 3 or 2. There's probably variation in this, but 4 is definitely, and all the random forests has just destroyed it. So what we're gonna do, we're gonna take and go over here, and let's go to random forest right here. Oh, we can't get that. There we go. And so we've got the number of variables being tried, but we should have more parameters we can do for the random forest. We got here mtry right there. Let's go. And I want to do a boosted tree also. Let's do a boosted GBM. So here's our GBM right here, and there's the GBM tree. Cool. Awesome. Let's go ahead and grab a GBM. Okay. So it's basically the same code. I mean, I guess all we really need when you think about it is we're just going to be changing this right here. So let's grab the tuning grid. So here's the tuning grid right here, and we're just going to change it to a GBM. So this is the fun and ease of making models, is it's like, well, just grab your parameter grid if you don't want to rewrite it, because it's so easy to make a mistake like n-trees or n-tree. Random forest, I think, uses n-tree, so that's the easiest mistake to make. So we should be able to, like, you can always look up your tuning parameters if you get stuck on them, but we should be able to add in another tuning parameter right here, this one, and this is where people get confused, is it should be n-tree equals concatenate, and let's do 100, 500, 1,000 trees. It should like that. Should have columns only. Where did I make a mistake? Oh, we don't worry about this. So should have columns mtry. Well, didn't like that. Sorry there, tuning grid on that one. Let's hop in the big one. Let's just go to the big leagues. No worries about it. Here we go. So here's our number of trees we're using for our boosted trees right here, and let's do that. We got our tuning grid, and then it should just be gradient boosted models right here. So let's grab the code, and let's grab it like this. Let's take it, let's drop it in here, and let's go here and go to GBM, and let's go to here and go GBM, 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 GBM. Cool. So error, the tune parameter grid should have columns, entries, interaction depth. What does it not like? Shrinkage should have columns, number of mins bios. What error did I make? Entries, interaction depth, shrinkage, and min bios. Oh, I don't think I read the tuning grid. Oh, you know why? This is parameter grid. It's got an M in it. Oh my gosh. It's the smallest things. Smallest things. You're like, well, why doesn't it like it? It's because there's an M. Because I was like, it has it. It has those things. And thank you so much. I love it when it tells you what it should have. It's like, here's the things it should have. So it's like, awesome. So we go ahead and take a look right here. This one might take a moment. We'll see how long it takes. But we're going to look at how the boosted tree does, because we just got back that the forest did really well. So the forest did really well. So now our goal is to try a boosted model right here with trees learning from trees. So will the boosted model beat it out? That's the question of the day. Will the boosted trees actually learn? Now, what does each of these do right here? We've got right here, and we didn't do extreme gradient boost, and that's where I get crazy. So we've got here the number of trees. This is just how many boosted trees we will build. So we'll build 50 trees, 100 trees, 500 trees, 1,000 trees, 5,000 trees. Interaction depth is how big they will grow each time we build a tree. Will we have 1 interaction, 2 interaction, 3 interaction? So it's how many splits we'll allow it to do. We have shrinkage right here, which is how fast it learns, the learning rate, either a fast learning rate or a slow learning rate of how it learns the relationship. Number of min observations in node is the number of minimum individuals that can be in a node at the bottom. Once again, we got y tilde x. There's your y tilde x, comma data equals. Here's the method right here that tells the caret package which method it's using. This is why caret's amazing, because you don't have to change much of your code to run anything. You've got here the tuning parameter equals param grid. So there was a small change in the spelling right here. Previously it was paragrid. Doesn't matter, it's just got to call it the right thing. So you can call it whatever you want. We've got the train control equals fit control. I've just got time to talk about this because it hasn't finished running yet. Train control equals fit control. And so that's the fit control we set previously, which is controlling the k-fold cross-validation. If you do repeated k-fold cross-validation, it'll take more time, but you'll have a better estimate. Verbose equals false. If verbose is equal true, you'd see a bunch of output flooding the screen down here. Probably literally it would just be like flood of output. And then preproc center scale turns things into z-scores. So wow, the GBM is taking a moment. This is a very complex model, and especially with the higher order tuning grid, that's why you're often seeing these things take a lot more time too. This is a really big tuning grid. So big tuning grid, lots of models being tried. Let's see how many models we're trying. So here we have 1, 2, 3, 4, 5. Here we have 2, and these are not the models, it's just the number of different things. Here we have 4. Here we have 3. Pause the video if you're watching right now and figure out how many models are being tried. I'm going to try to do the math in my head, and it looks like we have 120 different models being tried, because that's 5 times 2, which is 10, times 4, which is 40, times 3, which is 120. So there's 120 models being tried right here with different combinations of these. Like there'll be a model tried with 50 trees, 1 interaction depth, 0.001 shrinkage, and 1 in the min nodes. And then we'll try it with another combination of all these. And if you can tell, this is why model building can take a moment. We'll probably end with this because I've went through everything here. How many people do we have watching? How many people do we have watching? Say hey if you're in the chat. How many people? 4. That's awesome. I like it. So I'm glad we got people still watching. So we had up to 9 people at one point. I don't know what I did, but I must have answered all the questions because they all left within they left around 1, maybe class. It's so cool, like watching it. So if you're here, say hey, and let's see. It's still not done yet. I guess the biggest thing is we're writing the questions for the final. The final we're looking to have open for 2 days. So I'll send out announcements about this. We're trying to get it all finished up with the code and everything, or not the code, but we'll send out the final for 2 days will be open, and also the take-home for 2 days will be open. So you'll have 2 days to do both. The take-home should be out by the end of this week, and you'll have 2 days to do it. Don't talk to your friends. If you have questions that are kind of general questions, ask us. And come on, GBM, you can do it. I want to know how it does. We were at 91.7%, and the standard deviation for it was like 0.7% or so. So I need to really get above like 92.5. Let's see right here. Let's do the math in our heads or use the calculator. In the previous output, the best model was an accuracy of this. So the coding night should be available on Friday. Yep, it should be available, and we're going to try to have it open for like 2 days, and then you'll have 2 days to do it and ask questions. But once again, only ask us, and we'll talk in generalities. This GBM will have been worth the time if we get an accuracy above 92.3. If we can get an accuracy above 92.3, this has been worth all the time. And this is why sometimes you just use a random forest, because GBMs, and we didn't do extreme gradient boost, and we just did gradient boosted models. So we'll see how this does right here. See if it actually was worth the time. I don't know. How's everyone doing? Evan's in the chat. We'll see. Can you believe this, Evan? I mean, I am streaming on the computer. I am uploading to the internet while I'm doing this. This is a very, very good computer. You can do it, computer. You can get through the model. Can you think about all the equations the computer is solving right now? All the things it's trying. Oh, I thought it went away. We'll give it like another, maybe, I'll give it till 124, and if it doesn't do it, I'll say, well, we'll check back on it, and I'll give you guys the update. Once you get like 97%, like, you'd be like, no way. Like, how did it do that? And then we got to see how it did on the holdout. So then we have to see if it's overfit on the holdout by using, so let's go ahead and grab that code. You ready? So we should be able to use the code we wrote earlier. We should be able to use the PostResample code right here. And it's really going to come down to the forest and the GBM. Like, the forest is already winning. The forest is in first place, and GBM's coming in here at the end to be like, well, let's see how I do. So we go here and we grab this, and we can take this model right here. Good. There's how the forest does, and then we haven't even looked at our GBM yet, but you notice the only thing I'm changing right here is the model that is making the predictions. I worry about my computer crashing when we do this. I know, right? Your computer will start to go. So I've totally seen that. My little laptop will do that, but yeah, this computer right here can handle it. It's just taking its time. It's got all the good RAM and all the good stuff in it. Got a good processor, good video card, but if a computer like this takes a while, that's why sometimes you just run these things overnight. Like, truthfully, the problem with your tuning grid is this, Evan. Your tuning grid grows at an exponential rate. If you were to just add, like, if you were to double the size of the end trees, then you would have 240 miles. You would double the size of your tuning grid. If all these tuning parameters were 5 in length, that'd be 5 to the 4th power, which 5 to the 4th power is 625. Now, they're not all 5 in length, but if you just did 5 tuning parameters for each one of these, you'd have 625 models. 5, 20, 5, 25, 125, 625. So you'd have 625 models, which is insanity. And, I mean, you can do it. It's just going to take a while. It's going to take more than 5 times longer than what we have going on right here. It'll take like 5.1 times longer. And so, I don't know if I can do this mustache, everyone. It's getting to me. I don't know if I can do it. We're reaching my threshold of the to be continued on this, Evan. And if anyone else has any questions, did the activity make more sense right here, Evan, Joel, or anyone else still watching? Does the activity make more sense? Do you know what's going on with it right here? I think we're gonna have to do a to be concluded on this right here. But does it make more sense right here with what's going on with this? And yes, you know what you're gonna have to do? You're just gonna have to use your imagination to figure out what's going on right here. You're just gonna have to use your imagination. So there you go. I think that's got it. I think I might head off because I want to know what it does. I'll give an update tomorrow, and it's thinking away. It's got away. It's gonna do a watch in 3, 2, 1. Nah, not happening. Okay, so I'm gonna head off right here because I gave a 124 deadline on this model working, and it didn't meet my deadline for working. So this will be the end of the stream. Come back, say hey. I'll see everyone in class tomorrow, and that's got it for now. Watch later, and the stream is gonna finish. So see everybody later. Bye guys. Bye Evan. Bye Joel. Bye everyone else who's here right now. See you guys. I'm not joking. I'm not joking. Oh, the rainbow's still on because I have it on there. I'm not joking. It literally finished. I said I would end the stream, and it did that, and it's 124. Everyone probably left, but it literally did. I went to itch my nose, and I end the stream, and I look, and I'm like, of course it finished. Of course. Well, we have to put it in the stream how it did. So how's it doing? So the shrinkage, the accuracy, all that time, and it didn't meet our threshold. It had to beat 92.3, and there's the number right below it. All of that time was spent, and no. But now we have to see how it does. Each of them do. Now remember, forest can be overfit. So here's our forest model. Fixed city not found. Oh, because we're... Oh, it's on holdout. Oh, we didn't use a holdout. We can't do it because there's no holdout. Well, we don't want to... It's going to overfit to its original data. So I'm bummed now. So we don't even know if the data is overfit. So it's, yeah, we can't actually get this stuff right here because we shouldn't do it. It'd be bad statistics. So we did not actually use a holdout. So maybe I don't know. It's very hard to say what won out here, but the GBM probably wasn't worth our time, and we didn't do a holdout, so we can't actually check to see how the holdout's doing. So that's got it. Let's head off right here. The GBM wasn't worth the time. Yeah, this will be what coding night's basically like making different models, a lot of copy paste. So I mean, that's what you do in code. You copy paste stuff. If it works, you take it, you use it again. So that's got it. Let you knows again, and then we'll head off. So goodbye, everybody.